Okay, so let's review the content of the class up to now. So we are sharing the planet with easily 8.7, 8.9 million species. We also know that the evidence suggests that many of these species are now declining and many of them are going extinct. Today, we're moving to the next phase of this class, which is to find out why. Why are these species declining? We're going to be reviewing one of the underlying causes of this decline, which is called overexploitation. So let's understand today I want us to understand what overexploitation is, what does it do to a species, and why are we doing overexploitation. So overexploitation, if you were to look at the definition of overexploitation, is defined as the unsustainable hunting, fishing, or extraction of raw materials. Okay, that's the technical definition. Again, it's unsustainable. That's again the keyword there, extraction of raw material. Another definition that I like potentially more is the second one, which is exploitation of a wild population beyond his natural level of replenishment. Take a moment to think about that definition. Exploitation, meaning we are taking something out of that population beyond his natural levels of replenishment. Okay, so I want you to think about this like you have money in your bank. Basically, you are taking more money from the bank that you are putting in. The result of that action of you taking more than you are putting in is that your statement is going to go down, your balance is going to go down. So it's the same thing for a species here. We are over exploiting whenever we are taking more individuals from that population that the population can produce, and the consequence of that, of course, is that the populations are going to decline. There are hundreds of case examples of species that are being brought down to the brink of extinction because of this issue of overexploitation. Here are just some case examples, and you can appreciate the magnitude at which we are exploiting these populations, and then it just makes sense that these populations are unable to replenish the individuals that are dying, and as a result, the consequences, one of the consequences, of course, is that the populations will decline. I want us to understand, before we get to see how overexploitation works, I want us to understand how do you regulate the size of a population. When you look at a population, basically how many individuals are there of a given species, how those numbers come to be. So at the most basic level, the number of individuals that you see in a population is the combination of a couple factors. One is what is called the input of individuals, and the other one is the output, right? Makes sense. The balance of how many individuals you have there is basically the balance between how many you get in and how many do you get out. In the input, we have two demographic factors that are important. One is natality, which is basically how many individuals are born, and the other one is immigration, which is basically how many individuals arrive. That's the reason why it's called input. How many individuals are you adding? The way to add individuals to a population, again, is by new individuals being born or new individuals arriving from somewhere else. Now, in the output is the opposite. You got to think about the output. What is taking individuals out of the population? And the only two demographic processes that can do that is mortality, individuals dying, that takes individuals out. And the other one is migration, which is basically individuals leaving. Mathematically, there are different ways to formulate this. And let's break it down into the pieces, right? So one of the different ways to model the size or the change of populations over time is what is called density independent growth. Okay, think about that, density independent, basically, and growth. Basically, what it suggests is that the growth of the population is independent of how many individuals are already in the population. There is something that I want you to, mathematical term that I want you to pay attention to, which is this value here called R. R is defined as the population growth, right? Again, population growth is, from the term itself, is whether the population is increasing or decreasing. And that mathematically is defined as the combination of the four factors that we just saw. Basically, natality plus immigration, that's the reason why they are positive. You are adding those, minus mortality minus immigration, right? Again, natality and immigration add, mortality and migration remove. The balance between that gives you R, which is the growth of the population. Now, what about the population size? We're not interested on the growth of the population, but what about the size itself? If I want to know what is the size of the population tomorrow, how do I figure that out? Well, mathematically, that's done with this mathematical equation here. So the size of the population at a time t+1 means time plus 1 generation, is going to be equal to the size of the population now times the size of the population now times r. Okay, I know that many people get scared with mathematics, but this is actually pretty simple. Let's do an example here, and let's imagine that the population size is 100, just to make things simple, right? So there are 100 individuals, and I tell you that the growth of that population is 10%. Basically, the combination of these four factors here gives you a growth rate of 10%. So if the population right now is 100 and they grow at a rate of 10%, that means that the next generation is going to be 100 times 10%, that will be 10, plus 100, that basically suggests that the size of the population at a time t+1 is going to be equal to 110 individuals. Let's look at some examples here. Again, I just did three case examples for you to see here over time. And here is the actual table and at different populations at different times using different growth rates. And again, let's just do quickly an example here. Here, this population is growing at a rate of 1.1, which is 10%. So, and at time 0, the population is equal to 10 individuals. So that means that at the population, that population at a time t+1 will be 10% of the population now, which will be 1 plus the 10, that will be 11. Okay, and basically what you get is this growth rate here, and you do that for every generation, and what you ended up getting is these curves that look here. So this, for instance, here in red is a population growing at a rate of 30%, and this one in green is a population growing at a rate of 10%. So you can see is a population that grows exponentially, and that's the reason why it's called density independent. You see that there is nothing on this equation controlling the size of the population, and that's the reason why the population skyrockets, right? Well, I want you to think about how real that could be in nature. Can a population grow forever, right? I hope that you say no. And as a result of that, mathematical people back in the day thought, yeah, that cannot be true. The populations can just not grow forever. That there gotta be something then that controls the size of that population. And that led to people to create what is called density dependent growth. So again, what you see now is density dependent, meaning that the growth of the population is gonna be dependent on how many individuals are there. And what they did was to use the same mathematical equation, but now they add another term which includes what is called carrying capacity. That carrying capacity is denoted with that value K in this equation here. Let's break it down into pieces, and let's do a quick example here. And let's say that the population has 100 individuals, and the carrying capacity of the environment is also 100 individuals. Carrying capacity is how many individuals an ecosystem can contain, right? So if there is a space only to have 100, then the carrying capacity will become 100. So let's do it quickly here. So if I tell you there are 100 individuals and the carrying capacity is 100, so 100 divided by 100 will give you 1. 1 minus 1 will be 0. 0 times all of this will become 0, and basically the population will not grow. You get that? And the reason why it doesn't grow is because the population is already at carrying capacity here. So let's now look at the consequences of us having that carrying capacity in the mathematical equation of density independence, right? So all that part of that equation here is what is called density independent. Now that I added carrying capacity, it becomes density dependent growth. So now you can see here is the consequence of us having that term here. Basically, you see, it's the same data that I showed you before. Here's an example of a population growing at a rate of 30%. And you can see how the population settles at the carrying capacity. In this example, I set the carrying capacity to 150, and this one to 100. And you can see how the population always stabilizes at carrying capacity. Just for reference, I also use the density independent growth of this population at 30%. Right, so you can see in red here, that population is growing at 30%, skyrocketing in density independent. But when I put carrying capacity, that population is going to stabilize at the carrying capacity. So in this case, the carrying capacity, I set it to 150. In this one, I use 100. And in this one in green, here at the denominator, I put 50. And then the population stabilizes there. All right. So again, this is just the mathematical way for us to assess how the populations change over time. Now, what about, okay, this is natural, right? This is what happens in nature. Now what we gotta do is to figure out what happens when we start killing these animals. We're killing them because we are eating them or doing certain things to those species. So basically what happens is that to this equation of how the population changes, we had to subtract what is called fishing mortality. Fishing mortality becomes another ratio, right? It's basically, sorry, another fraction. Basically, how many individuals, what proportion of the population we are killing, and we multiply that by the carrying capacity, and we remove that number from the size of the population. So here is an example. Again, let's just look at a population that is growing density independent at a growth rate of 30%, and I put a carrying capacity of 50. And here what I did, I took that population that is growing density dependent, carrying capacity of 50, and then I here use different fishing mortality. So when I said fishing mortality to 0, here all of these things become 0, and basically the population grows up to carrying capacity, up to the carrying capacity here. So like you can see here, for instance, if I use fishing mortality to 0 in this example, the population settles at a 50, which is again the carrying capacity. Now, if I use fishing mortality of 0.3, 13%, you can see that the population stabilizes at the original size of the population. So the population basically don't grow. This is a case example with a population that is growing at a rate of 30%, doesn't grow at all when the fishing mortality is 30%, but the population will decline if I fish the population at the same rate that is growing. And this is one of the things that is interesting for you to realize is that when I kill fish, in this, well, let's imagine that this is fish, at the same rate that the population is producing animals, the population will decline, right? And the reason for that is because there is a time that the species need to get to adults for them to balance out things. But the important thing for you to realize from this comparison here between fishing mortality and growth rate is that normally for you to maintain the populations stable, you need to fish the populations at a rate of about half the growth rate or lower. Okay, so you can see here in this case the population remained stable, relatively stable at the first size when we fish that population at about less than half the growth rate. That's what I want you to realize, is that if we want to maintain a population that doesn't collapse, we had to kill individuals from that population at a rate below half the growth rate. If we do it higher than that, the population is incapable of supplying the individuals that we are taking off, and then taking out, as a result, the population will decline. Now, that, again, I want you to remember that. We need to kill individuals at a rate of half the growth rate or less if we want those populations to remain stable, okay? Now let's see what happens in reality. Here is a case example. This is a paper that Christine Warpage and I did back in the day in +1. And in this paper, we took different populations of sharks and we look at the growth rate, all right? So you can see here, for instance, different species. This species, for instance, has a huge growth rate. It grows at a rate of 12% per generation. But then you have things like the whale shark, right? Whale sharks are huge. The growth rate of that population, again, is less than 4% per generation. So it grows very, very slowly as a population. Now, as I told you, if you want to fish these populations in a way that is sustainable, you need to kill them at least half the growth rate. Basically, what happens is that if we want to sustain these populations, we need to fish them at these lines that you see in red here. Again, killing the fish at about half the growth rate if we want to maintain them. Okay, now the reality is, let's look at what the actual fishing mortality is. Again, this is the fishing mortality that will be necessary for us to prevent the populations collapsing. But what happens in reality is this: the fishing mortality of those populations is easily 46%, right? So you can imagine this is what the populations can sustain being killed without collapsing, and this is what we are actually killing them at, twice. In some cases, twice, 3 times the growth rate. So it's no surprise then why many of these species are at the brink of extinction right now. Almost, as I say, these are species from the Caribbean. Almost all of the species of sharks in the Caribbean, with the exception of a couple species, are almost at the brink of extinction. They have been wiped out from the entire Caribbean, again, mostly because they cannot withstand these levels of fishing. And again, that helps you to explain how is it that overfishing leads to the decline of these species. Now, how bad is it? Okay, so that is how overfishing or of overexploitation is leading to the decline of a species. How bad is this problem in nature for all of the species? So here is an example of all of the fisheries in the world. All of them is a very famous paper by Red Waxon and Professor Pauli, and they analyzed the fisheries over time, going back all the way to the 1970s, even before you and I were born. But you can see that populations, we were able to get a lot of fish out of the oceans. You can see how it went up, but turns out that there was a moment back in the 1980s when the sizes of these, the amount of fish that we could take from the oceans started to go down at a rate of about 0.7 million tons a year. That's a lot of fish now that we are not able to catch from the oceans, despite the fact that we're actually now doubling the amount of effort that we are putting to catch these fish. And that is already one of the first signs that we are overexploiting in this early phase of exploitation. We overexploited these populations to a level now that they are just coming down again, because unfortunately we are killing more than the individuals that can be produced. That explains then why the populations are declining. It has been suggested already that the magnitude at which we are taking of all of the biomass that is produced in the ocean, of all of the energy that comes from the sun and is processed in this planet, we are already, as humans, we are easily already eating 24 to 35%. Okay, this is what I want you to think. This probably doesn't look like much, right? But we are just one species out of 8.7 million species. And of all of the productivity of the oceans, we're already easily eating over 35% of that. This is like us having a cake that we have to share with 8.7 million species, and we alone are eating already 35% of it. Unfortunately, we are becoming so greedy at exploiting and killing and eating the fish from the oceans that we are just seriously not thinking about what is left for future generations. These here are the statistics of all the fisheries in the world. What I want you to pay attention to is the fact that today there are over 28% already of the fisheries overexploited. Overexploited, again, is populations that are being, in which we are taking more individuals than the individuals that can be replenished naturally, and 52% of them are fully exploited, meaning that we are already at the level of that those species can take. So here easily you can see that up to now, our generation, we are easily taking 80% of all of the fisheries in the world, and we are basically just letting for future generations 20% of the fish to be fed on. Professor Boris Worm from the Housing University took all of this data and he broke it, rather than looking at the total catches, he analyzed it by species, the different stocks that are being fished, and he analyzed the extent to which fisheries are collapsing, basically a point in which the fish can just simply not produce more fish. And he found this figure here, which is this dotted line. This is the rate at which stocks are collapsing. Collapsing again, meaning that you cannot take fish anymore. Even if you go and fish, the fish are not there to be caught. And what he did, he extrapolated this line, and what he found was that easily by 2048, we could run out of fish to eat from the oceans. I want you to go and Google fisheries 2048, and you will see a lot of news articles about this professor, because it was shocking to know that the degree at which we are taking fish out of the ocean is so massive that so many populations are declining, and forget about feeding the future populations. So there are many examples. Again, that's just on the fish. On land, the thing has been even worse. As I mentioned to you, unfortunately, most of the largest mammals on land were long gone, mostly because of overhunting. And there are many examples, again, including plants and things like that, that are related to a species that had gone extinct because we overexploited them. Again, the underlying reason why they went extinct was because we just took a lot more individuals from those populations that the populations were capable to replenish. Now, why do we do this? Okay, so that's the second thing that I want you to take from this lecture. What are the reasons for why we do this? There are certain things that I find remarkable, and I don't think there is an excuse. And one of them is culture. For cultural reasons, we are overfishing, exploiting a lot of these populations. So let's check out a video about that.
In the back room of a Beijing restaurant, I'm getting a taste of China's, well, let's call it eclectic culinary cuisine.
Lots of food here. Mr. Chen just told me that this is stud bull penis, this is deer penis, these are lamb testicles, it's Russian dog penis, and this is just deer meat venison.
Exotic maybe, but perfectly legal, so far.
Now, Mr. Chen, if I wanted to order some tiger paw or tiger penis, can I order that here?
He tells me they do not have it because the tiger is a protected species.
Say tiger paw here and tiger penis.
They use the name, Mr. Chen says, only to impress their clients.
When we see tiger paw and tiger penis on the menu, Mr. Chen, though, is adamant that they don't have it here, and that's just a name. They won't let us back in the kitchen to actually see for ourselves.
There's no way of knowing if indeed this restaurant serves tiger, but we do know it's happening throughout China. According to Wildlife Alliance, China is the #1 destination for tiger and other endangered species. Fines are stiff, around $14,000 if you're caught trafficking, so the practice has gone underground. It's 5:30 in the morning in the southern city of Guangzhou, and business is booming at this illegal trading spot. We're trying to stay out of sight, but our cameras pick up images of vendors selling from the back of their vans. I'm with Craig Kirkpatrick of the Wildlife Trade Monitoring Network, Traffic. We decide to get out of the van for a closer look. Our arrival isn't well received. Dealers quickly disperse.
Look over here. Hey, Craig.
But we are able to catch a glimpse of some of the illegal activity, the sale of ferret badgers and civet cats.
Civets, little baby civets here, and then the cat.
The consumption of these animals is believed to be the source of the SARS outbreak in 2002, which killed at least 700 people around the world. Despite a crackdown by the Chinese government in 2003, the illegal consumption is growing again.
So they're buying it because they want to eat the meat?
Exactly.
They're buying it for medicine purposes as well?
Yes, it's more of a generalized health tonic rather than a specific medicine prescribed for any particular ailment.
Walking the legal markets in Guangzhou, it's easy to see why overexploitation is the #1 threat to China's animals. Thousands of turtles, poisonous scorpions, and snakes fill the stalls. Dried bags of seahorse, shark fin, and deer tails pile up along the streets. There's even pillaging from other countries to satisfy the almost endless demand.
It truly is a global trade, coming in from Southeast Asia or from the United States.
In this stall, endangered turtles from Madagascar. For sale here, illegally.
This is illegal. Are the police going to come here and shut a place like this down?
There's so many other priorities that they've got going in this very large country that's expanding at a tremendous rate. Wildlife trade just doesn't really register very high on their priority list.
These animals aren't.
So right there, you can get to see an example in which is culture one of the underlying motivation for this overexploitation. And before, I know that many of you are probably becoming very judgmental of those Chinese doing that crazy thing. But one of the things that I want you to realize is that we do that is exceptions of exploitation of a species for cultural reasons everywhere. For instance, here in Hawaii, it's common to see exceptions for you to go and fish certain fish if you are a native Hawaiian, right? So I don't have judgment on that. That's a cultural thing and people have the right. But what I want you to think about is about the fact that then we cannot go and judge these people on those places. The other thing that I want you to realize is then how the fish doesn't care. If it was killed by me, by the Pope, the fish is still dead. So culture, despite the fact, again, I'm not questioning any of the reason for why we overexploit a species for cultural purpose, but what I'm saying to you is the fact that for cultural purposes, as for the fish goes, it just doesn't the fish just doesn't care. And there are, again, hundreds of species that today are being overexploited just to supply or to satisfy these cultural reasons. Again, everything from the whale hunting, sharks, again, all the way up to jacks and serranids and fish here in Hawaii as well. Again, just for you to generalize that, for us not to be judgmental, again, for the cultural reasons for which other cultures do over exploitation, because we do it here as well. So we need to be straight with the double standards at which we judge the reason for why species are overexploited for cultural purposes. So the other reason why we overexploit a species is basically food. The size of the world's human population is increasing quite dramatically, and obviously, if you think about the fact that there are almost 8.7 billion people on the planet, all of that people gotta eat, and the amount of food that every human being requires to be well is just skyrocketing. And here on this figure, you can see the global food demand of humanity, and you can see how the amount of food that is required is just skyrocketing, and that food has to come from somewhere, and unfortunately it gotta come from a species, wild species, that can supply that thing. And that's another reason why many species are being overexploited, which is to satisfy the increasing demand for food. Now, you will think this, and this is what I want you to realize, that there is something kind of evil about the human systems that leads to the overexploitation of a species. I want you to think about this. So if a species is declining, we go and fish, and the species is declining, you will think that there is going to be a moment in which it's going to become very expensive for us to go and fish something that is not there anymore because we overexploit it. It turns out that the opposite things happens. The lower the population go, the more we go and fish. And that's kind of sick, right? Like, you will think that from the economic perspective, overexploitation will take care of itself, because again, when the populations start declining, the individuals become so rare that there is just no profit for you to go and do it, and people will move somewhere else, which will allow the populations to recover. But that doesn't happen in nature. Pause this video now and think about why. Why will we go and fish more something that is already declining, that economically probably is not profitable at all? So there are two reasons for this. One is what is called subsidies. Governments, especially governments from the developed world, including the United States and Europe, we are concerned about the level of employment that these fisheries provide to societies. As a result, we subsidize this. So many of these companies that go and fish, they are on a loss already. There is just not enough money that they can make out of the fish, so they get subsidies from the government. And the reason why the government subsidizes is because they are afraid of losing all of those livelihoods there. So that's another way how populations fail to escape fishing, is because we sustain fishing even despite the fact that economically it's not profitable. Another reason is the fact that we value what is called rarity. This is a very famous paper by this professor, by this person here. I don't know this person at all, but it's one of the few papers out there that document another issue for why do we continue to exploit species despite the fact that there is nothing else to take out of them. Again, as I explained to you, if this is the size of a population, you will expect that as the population goes down, the profit will go down. And at that moment, the people will get out of the fisheries because there is no money to make, which will allow the population to recover. But as I say, that doesn't happen in reality. And again, one of that reason we explain is subsidies. The other one is what is called rarity. As the populations start declining, right, what happens is that they become rare and people want them even more. And basically what happens is that the price of those species go high. A good example of that is, for instance, the tuna fish. The tunas, the bluefin tuna, is a species that is skyrocketing the price. In fact, there are some videos, documentaries pointing out how companies in Japan are buying tons of these fish and putting them in refrigerators with the expectation that the fish will go extinct, because that will make the price of that fish tuna super high. So here is an example, though, that was used on this one paper, and is related to this species Avalones here. You can see how this is time, and this is the size of the population and the price. You can see how the size of the population start declining, but then the price of that species went up. And you can see how the population never managed to recover. The expectation, again, that the population will recover once the price is low, just doesn't happen in nature. Again, it's just because the price goes up, and that increase in price then allows people to invest even more to go and catch the few individuals that are left, and as a result, it creates this thing that this person called a vortex, an extinction vortex, in which again, as the species goes down, the price goes up. That allows people to go more, and the fact that they go even more makes the population even go lower and lower, making the price higher and higher, and basically creates this vortex and a spiral that creates this self-feeding mechanism that led to the species to go extinct via overexploitation. How common is this problem? Well, there are hundreds of examples of this problem. Here you can see, for instance, the price of species that are used for collection, like butterflies, and you can see how the species that are rare are commonly more expensive than the species that are very abundant. And again, just documenting or value for rarity. Again, the more rare the species is, which is a species that we probably should be taking care of, unfortunately, those species are also very expensive, and as a result, we just go and exploit them even more. People is willing to take the chance to go and get that, given the return that they get in economical terms. And here is another example with another mammal. Now, this issue of rarity, the value of rarity, actually allows for even things that we think are good to be things that actually are bad. Let me just give you an example. There is this thing called CITES. CITES is an international law that was created among an agreement among the countries of the world to prevent the traffic of species between countries, species that are put on that list. So a lot of NGOs work very hard to put species into those laws, cities, such that now that will reduce the demand. Just think about, for instance, people in Japan wanted to eat whales, and if now the whales are on cities, that means that other countries that catch the whale cannot ship it to Japan, and by cutting that supply, governments of the world were hoping that it would prevent that exploitation on those countries, allowing the species to recover. That was the motivation of this law, CITES. And there are hundreds of species, again, that people is making an effort to be put into this law, again, just to prevent the transportation between countries of this, which will hopefully allow the supply and demand issue and allowing the species to recover. That was the original motivation, pre-novel, right? It turns out that that had the opposite consequence on nature. Actually, what ended up happening is that those species that were put on this list actually start being exploited even more. The reason for that is that the price of the species became higher, because now you get caught with this thing, you go to jail. So now people were willing to pay even more. And here you can see examples, for instance, of a species that are in danger right now, the ones that are put in CITES, against the species that are not included in CITES. Let's look at lizards here. You can see how the price normally of the species that are put in this law is higher than the species that are not. And this increasing price, again, allows people that traffic into these species to take the risk of just going and getting, because you get twice the profit of another species that is not in CITES. So again, this issue of rarity may even things that we think are good into things that are not good, because again, when you put protection into place, basically there are higher penalties to people, meaning that there is a higher risk. And if there is still a demand for this, there is always going to be a supply. And in this case, when those species are put into these laws, the cost of that supply and that demand becomes much expensive. Now, unfortunately, the species will have unintended consequences when we fish them or we overexploit them. One of them is that they become smaller. This is a paper by Professor David Conover. I think that he's in Stony Brook when he did this paper. Professor Conover took this fish, the Atlantic silverside, and he started the populations, all of them at the same size. He had these big aquariums. They were normally 3 treatments. And in one of the aquariums, he got and caught the smallest fish. So he went through that aquarium and he killed all of the fish that were small. What happened on that aquarium is that the fish became bigger, right? So you are killing the smallest, the ones that are big are surviving, then the individuals became bigger. In the opposite, in the aquarium that you took the largest fish, the population, the individuals became smaller over time, right? So you are killing the bigger fish, the species doesn't want to become small, large anymore because they are dying. The ones that had the advantage to survive are the ones that are smaller. So not surprising, the populations became smaller over time. This is the number of generations. You can see that the sizes of these populations shrunk quite dramatically just 4 generations later. In the middle is the fish that were caught randomly. So if you were to catch fish randomly, the population doesn't change the size. Now, when you think about fishing, normally what we do, as we established in the class before, was that we normally like to get the fish that are bigger or very abundant. And normally what it means then is that, and that's mostly what happens on the fisheries, we normally get the largest fish. So what is happening in the oceans is that the fish are becoming smaller. So here is an example. This is a paper done by Jeremy Jackson from Scripps. He was one of my supervisors there when I was at the University of California. And this is an example with the cod, I believe. And this is the example that I told you earlier, in which showing how this species back in the day was easily 4 feet long, 120 centimeters, which is like this big. And over time of us fishing these fish, the biggest ones, the populations became smaller. So now that those individuals are this big. So basically, one of the consequences of this massive fishing, documented with experiments and with real data, is that the fish are becoming smaller, right? Because again, we're catching the bigger fish. Now, the problem of us leaving the individuals that are small left is that when they reproduce, normally they produce less eggs, and eggs that had less quality to survive. So here is an example. There are hundreds of papers documenting this. You can see the size of the fish against the size of the eggs, and you can see that normally the fish that are bigger produce not only bigger fish, larger number of eggs, but also eggs with more yolk in the eggs, which allows the juveniles to survive even better. Just think about that, right? So you had a humongous fish, it has the capacity to produce bigger eggs, and the juveniles had a lot more food to feed from those eggs, and they're gonna grow better and survive better. But when the fish become smaller, you get the opposite effect. The offspring that are produced are smaller. So now, unfortunately, again, when the individuals that are being produced become smaller, what it means is that they survive less. And here is the problem of what we were talking about, overexploitation. So naturally, what we humans do is that we are making the input smaller than the output, right? We are killing a lot more individuals that can be replenished from the population. But one of the unintended consequences of that is that the populations in return actually produce even less offspring, less quality offsprings to replenish the ones that we take out. As a consequence, there is what is called an extinction vortex. Extinction vortex again refers to this process in which the extinction of a species accelerates as a result of unintended consequences. In this case, again, we are overexploiting, meaning that we're killing more than the population can replenish, but by doing so, we are leaving individuals that are smaller, that produce less eggs, meaning that the population can actually replenish even less than they could naturally do, and that leads to, again, what is called an extinction vortex. Now, once the population gets to these smaller levels, again, when we deplete them, and the fact that they manage to produce offspring that are smaller, the consequence of that is that the population becomes smaller, and there is always a risk with those populations that are small. Basically, the consequence of that, or you having a population that has only few individuals left, is that there is less genetic variability. This genetic variability plays a fundamental role in sustaining the population. One of them is that it creates what is called genetic drift. So when you only have 3 individuals there, the genetic makeup of the species can go in any direction. So if there is a deleterious gene, for instance, that is damaging to the population, there is a chance that that gene can come in and take the entire population in what is called genetic drift, and that normally happens on populations that are small. In populations that are large, those genes are weird. They just don't take the population on weird and random directions. And again, the consequence of that genetic drift, talking about these extinction vortices, is that it makes the population even smaller. Now, The other risk of having populations that are small is that increases the risk of inbreeding depression. Inbreeding depression means that you are reproducing brothers with sisters, fathers with sisters. So there is a reproduction between close relatives. And the problem of that is that if there are genes on that population that are deleterious, normally they are kept on what is called a recessive form, right? The reason being, again, that if they are dominant, the individual dies. And that's the reason why many of these genes that are recessive can remain on populations for a very, very long time, is because, again, the individuals that are that have it die, and unfortunately, fortunately, when you have bigger populations, they fail to dominate. Unfortunately, when the populations become small, the chances of these deleterious genes to prosper increases quite dramatically, because again, when you have one recessive reproduce with another recessive, they become dominant. So that's how you can increase the expression of genes that are deleterious. And again, that's the consequence of what is called inbreeding depression. Is making, well, among several other consequences, is making these genes that are normally damaging to populations that are kept on a recessive form to have a higher chance of expressing, again, because you are reproducing close relatives. So a recessive with a recessive gives you a dominant, and that of course lead to the population to become smaller. So again, I want you to appreciate all of these unintended consequences of us driving the populations to these very low levels. Another consequence of smaller populations that had low genetic diversity is that they fail to have the genetic portfolio to cope with the stressors, right? So if you don't have the genes and there is a whole new different disturbance that came in, then there is a higher risk that the species can go extinct. Normally, when you have big populations, species had a hard time to go extinct, because among all of those individuals there are going to be a few of them with the genes capable of withstanding those stressors. But when the populations are small, the chances of those genes being there is very small as well. As a result, you maximize the chances of the species going extinct. Again, talking about here, we are talking about populations being overfished, which means that the populations are going to decline themselves. The populations themselves are going to create these self mechanisms that make the populations go even smaller and smaller. And the consequences of that then is that you are going to increase the risk of extinction of those species via, again, in this case, genetic mechanisms in what is called extinction vortices. Now, another consequence of, that's at the genetic level, what we just saw, another consequence of you bringing populations to a very low level is what is called deposition Ali effect, or inverse density dependence. Okay, so I want you to remember those terms: deposition or Ali effect. This term is probably the one that you see the most common. Basically, what it means is that when you have fewer individuals left, the chances of the individuals finding each other to reproduce reduces quite dramatically. Just think about, for instance, sharks. And the sharks normally are in thousands, but now there are only a few of them, one in the Pacific and the other one on the other side of the oceans. The chances of them coming together to reproduce decreases quite dramatically. And again, that is what is called the Ali effect, and it happens everywhere. Like corals, for instance, is another good example. Corals normally require individuals to be closer to each other, so that when they produce the eggs on the water, these eggs can come together with the sperm and reproduce. But when the corals that are left are so few of them, are so far apart, when they reproduce and release their eggs and sperm, that eggs and sperm don't find each other in the water, and that's the reason why, again, populations will decline as a consequence of this Ali effect. And again, is the fact that the individuals had a hard time finding each other to reproduce. Here is an example. There are hundreds of examples describing this Ali effect, but here just a case example. I believe this was with corals, and you can see how when you get 4 individuals on this example, the chances of reproduction, fertilization were 1, but when you get only 1 male in this case, the chances of fertilization reduce almost by half. Again, because 1 male alone has a hard time to produce enough offspring to colonize the females that are there. But this is, again, just one example, but it's, again, the principle of individuals having a hard time to find each other for them to produce offspring. Now, unfortunately, Once these species start declining, chances that they recover are very low. And we look at this mechanism before, what is called alternative equilibrium states. And we describe this, let's just describe it again, because it becomes important here. So it's the fact that you had populations already adapted to certain conditions, but when we come along and we fish those populations to a level, the populations will try to adapt themselves. Like in the example of the paper by Professor Conover, when we went and killed the bigger fish, the fish became smaller. That's adaptation. The genes that are leading to larger individuals are disappearing from the population. Those genes, once they are gone, they will never come back. So the population then will stabilize at that level. And obviously, if we continue to do that, there is going to be a loss of genetic diversity that leads to those three factors that we talked earlier about: inbreeding, depression, lack of resistance, and genetic drift. And again, the evidence for this, one of the best papers is a paper by Professor Hutchins from Dalhousie that showed that after you gave fish the time to recover, the fish never managed to recover. Now, another consequence of fishing, and we also saw this mechanism before, is what is called trophic cascades. And this is, again, there are very few of these papers, but this is one of the most important ones. This is by Professor Myers. Basically, again, I described this earlier, is the fact that when you get populations being overfished, like in this case, the sharks, as we saw earlier, basically we're just fishing these populations to the level that they cannot replenish themselves. They collapse, as you can see the example here. And the consequence of that is that the populations that they feed on then skyrocket. And here you can see the manta rays increasing, all of the species of manta rays increasing because the sharks are not there to eat them anymore. And as a consequence of that, whatever is being eaten by the manta rays declines. So again, another unintended consequence of this overfishing is what is called trophic cascades. Let's summarize the entire class. So again, we were talking about these individuals on a population, and they are regulated via the input that is based on natality and immigration, and the output that is based on mortality and immigration. Those are the natural processes that determine the size of the population. Then we come along, humans, and now humans, we become another source of the outputs. We start to take individuals out. While nature allows to take some individuals without causing the populations to decline, unfortunately, we do it too much into a process that is called overexploitation, which again is taking individuals beyond the natural levels of replenishment. Okay, and the consequence of that, the populations will decline, as you can expect. Obviously, you are taking more than the individuals can come in, and this decline of these populations then cause additional consequences on these populations, like deposition or the Ali effect. They also had genetic changes that leads to even further declines of the populations, and they are also what is called trophic cascades. So here you can see the ramifications of us overexploiting these populations, and then why overexploitation is one of the leading causes on the declines of a species, and how that is leading to the higher risk of extinction. And that summarizes the class for today.